Okay, I'm now recording. Okay, so last class we started talking about chapter 2, combinatorial methods. So we talked about how to find the probability of more complicated events using these counting methods. So one method is called the multiplication principle, right? And so it's the number of ways to select one element from each of k different sets, right? And so you just multiply the sizes of each set, and the product is the number of ways, right? So we saw the example of outfits, finding the number of outfits. We had an example where finding the probability of an all blue outfit was the number of all blue outfits divided by the total number of outfits. And so 2.2 is on permutations. And so we talked about the definition of a permutation. We listed permutations, and then we counted them without listing them. And so we also talked about how to calculate NPR for any given value of n and r. So this formula here is how to calculate NPR for any positive integers r and n with r less or equal to n. Okay, so this is all last class. Okay, and this is the notation for n factorial. It's the product of the positive integers from 1 to n. And 0 factorial by definition equals 1. Okay, and you pronounce it n factorial. Okay, and so then 2.3 was on combinations and the binomial coefficient. And so I just talked about the definition of a combination. It's just a set of it's just an unordered set of r elements. That's what a combination of r elements is. Okay. And so I gave an example of why this is called a binomial coefficient, because if you take x plus 3 cubed, you'll get an expression like this, and you can get the coefficients. The coefficients are just these binomial coefficients. Okay, and I told you the values of them for these. Okay, and so we're going to continue talking about combinations in this class and how to calculate them. Okay. So now we're going to start with we're going to continue 2.3, which is on combinations, the binomial coefficient. Okay, so this is example 2.6. And so A is list the combinations of 3 elements that can be formed from the set 1, 2, 3, 4. Of 4 elements. Okay, so let's do that. Let's list the combinations of 3 elements that can be formed from the set of those 4 elements. So a combination of 3 elements is just choosing any 3 of elements in that set and putting them into a set. So 1, 2, 3, 1, 2, 4, 2, 3, 4, and then 1, 3, 4 is another one. Okay, so these are all 4 ways to choose 3 of the elements in this set. The notation is of parentheses around. Okay, order does not matter. Okay, you could also think for every 3 that you choose from this set, there's 1 that you don't. So for 1, 2, 3, you didn't choose 4. For 1, 3, 4, you didn't choose 2. For 1, 2, 4, you didn't choose 3. And for 2, 3, 4, we didn't choose 1. Okay, so we didn't choose 1, 2, 3, and 4. Okay, so that exhausts all possible choices of 3 things from that set. So those are all the 3 combinations from that set. Okay, so B is count the number of combinations of 3 elements from a set with 4 elements. So it's the number of ways that you can choose 3 of the things in that set. Order does not matter. And so from A, the answer is obvious. There are 3 there are 4 combinations of 3 elements from a set with 4 elements. Okay, so there are 4 combinations of 3 elements. Is there a question? Okay, I don't know what that was. Okay, okay, so there are 4 combinations of 3 elements from that set. Okay, so here's a fact. If you take NPR, it's equal to NCR times RPR. Okay, and so here's a theorem. So the theorem is following. So NPR, N choose R, which is another notation for this, is equal to, well, if you take this equation and you solve for NCR, then you get NPR divided by RPR. So this is, that's this quantity divided by this quantity. Okay, so I just solved for NCR in this equation, and I got NPR divided by RPR. Now we know the values of the numerator and denominator, and so that's just N times N minus 1 times N minus 2 times ... times N minus R plus 1. Okay, and the denominator is just R factorial. Okay, so from last class, we talked about how to calculate permutations. And so the numerator is the calculation of this, and the denominator is calculation of that. And so we now have an expression for NCR, except we want to write it more simply than the way it's written there. So what you do is this. Here, you're multiplying the positive integers from N minus R plus 1 to N. And so continue multiplying the rest of the things after this to get N factorial. So far you have N times N minus 1 times N minus 2 times ... times N minus R plus 1. But then you take that quantity that we already have, and now multiply it by all the other terms. So N minus R times N minus R minus 1 times ... times 1. And so just continue to multiply everything and get down to 1. Well, if you multiply the denominator by that quantity, you need to multiply. If you multiply the numerator by that quantity, you need to multiply the denominator by the same quantity. And so I multiply the denominator by the same quantity. And so when you do that, the numerator becomes the product of the positive integers from 1 to N. So the numerator becomes N factorial. And the denominator has R factorial in it. And what you multiply the numbers from 1 to N minus R. So you multiply by N minus R factorial. And so then you get that expression. So NCR, also written as this, and choose R, is equal to N factorial divided by R factorial times N minus R factorial, that expression right there. And so it's you get that by solving for this quantity in this equation. It's NPR divided by RPR, and then you plug in the numerator and denominator, and then you write it in this easier to read form. Okay, and so that's the formula for NCR. So to give you examples of how to calculate this, for instance, if you had, let's say you had NCR where N was 5 and R was 2, then the formula tells you, okay, well, N is 5, so you have 5 factorial, and divide by R factorial, which is 2 factorial, times 5 minus 2 factorial. So then that's equal to 5 factorial divided by 2 factorial times 3 factorial. And that's equal to 5 factorial, when you multiply it out, 5 times 4 times 3 times 2 times 1, you get 120, 20, 60, 120. And then 3 factorial is 6. 3 times 2 times 1 is 6. 2 times 1 is 2. 6 times 2 is 12. So you get 120 divided by 12, which is 10. Okay, so 5C2 is 10. And see, that's one example. And another example would be, for instance, if let's say this was 4 and this was 3, then this would be equal to 4 factorial divided by 3 factorial times 4 minus 3 factorial from this formula, where n is 5, when n is 4 and r is 3. So you have 5 factorial over 3 factorial times 4 minus 3 factorial. And so then this is equal to 4 factorial is 24. 4 times 3 times 2 times 1. 3 factorial is 6. And 4 minus 3 factorial is 1 factorial, which is 1. So 24 divided by 6 is 4. And so 4C3, 4 choose 3 is 4. Okay, so those are 2 examples of using this formula to calculate NCR for values of n and r. And remember, r is at most at n. Okay, all right, so that's how to calculate it. So here's an example where we're going to use combinations to calculate a probability. Okay, so part A is going to be calculating a number, and part B is going to be calculating a probability. So example 2.7 says a poker hand is a set of 5 playing cards in a standard deck, in a standard 52 card deck. So I think I already told you what the standard 52 card deck consists of. I'll remind you, a standard 52 card deck consists of the following. So you have 13 different values, and those values are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. Okay, jack is usually abbreviated by a J. Queen is usually abbreviated by a Q. A king is usually abbreviated by K. And an ace is usually abbreviated by an A. Okay, so those are all 13 different values. Each distinct value has 4 suits. Okay, and those suits are hearts, diamonds, spades, and clubs. Okay, hearts and diamonds are red cards, and spades and clubs are black cards. Okay, so you have 13 different suits, and 13 different values, and each value, there are 4 suits. So for instance, a 9 has a 9 of hearts, a 9 of diamonds, a 9 of spades, and a 9 of clubs, right? And then the hearts and diamonds are red cards, and the clubs and spades are black cards, okay? Jacks, queens, and kings are considered face cards, okay? And ace is not considered a face card, right? So that's the composition of a standard 52 card deck. Okay, so for part A, the question is find the number of distinct poker hands. Okay, so we want to find the number of distinct poker hands. So imagine you had a 52 card deck in your hand, right? And it had all 52 cards in it. And then imagine you turn it over and you put down the table and you spread it out. So all 52 cards are on the table. Okay. So a poker hand is just choosing any 5 of those cards. So counting the number of distinct poker hands is just counting the number of ways to choose 5 of those cards of the 52. And so we already have an expression for that, right? That is 52 C5. The number of ways in a set with 52 things in it, in this case 52 cards, number of ways to choose 5 of them. Okay, so that's the number of distinct poker hands. The number of ways to choose 5 out of 52 cards in the deck. So the number of distinct poker hands is equal to 52C5. That's just another notation for it. And so then we just use the formula that I wrote down. So this formula here. And so use that formula there. You get n factorial, which is 52 factorial, divided by r factorial, which is 5 factorial, times 52 minus 5 factorial. Okay, and so then you calculate that. And this also simplifies when, even though we write the expression this way, the easier way to calculate it would be 52 times 51 times 50 times 49 times 48 divided by 5 factorial. So what this is if you take the 52 minus 5 factorial, which is 47 factorial, and you divide 52 factorial by it, so 52 factorial divided by 47 factorial, you're left with 52 times 51 times 50 times 49 times 48. So this divided by this is this. And then you have the 5 factorial in the denominator still. The easy way to remember it is 52C5, you just multiply 5 numbers in the numerator, starting with 52 and then decrementing by 1 each time. So 52 times 51 times 50 times 49 times 48. That's a product of 5 integers, decreasing by 1 each time, starting with the number here. And then dividing by 5 factorial, this is 5 here. Okay, and so you calculate that, you can use your calculator for this, and you get 2,598,960. So that's the number of distinct poker hands, 2,598,960. So that's the number of distinct poker hands. Part B is find the probability of a poker hand with value less than 10 for every card. Okay, and note that an ace will have a value of 1. Okay, so we're considering ace to have a value of 1. So the cards whose value are less than 10 are ace, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, jack, queen, and king have value 10. Okay, jack, queen, and king have value 10. Okay, so the values that are less than 10 are ace, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. Okay, so we want to find the probability of a poker hand with a value of less than 10 for every card. Well, we can start the way we often start, is by starting with some notation. So let B equal the event of getting a poker hand with a value less than 10 for every card. Okay, you could also abbreviate this as less than. Yeah, okay, let's just keep it like that. Okay, so let B equal the event of getting a poker hand with a value less than 10 for every card. The question is asking you to find the probability of that event B. Okay, so the goal is to find the probability of this event B. Okay, so to find the probability of this event B by our theorem, it's n sub B divided by capital N. And so n sub B divided by capital N, right, is the number of sample points in the sample space B divided by the capital N, the total number of sample points in the sample space. For this particular experiment, N sub B is the number of poker hands with value less than 10 for every card. Okay, and capital N, this total number of sample points in the sample space, well, that's just the number of poker hands. Okay, and so we want to find the number of poker hands with value less than 10 for every card divided by the number of poker hands. That's the probability that when you get a poker hand, that it's a poker hand where every card has value less than 10. Okay, so starting off with something easier, the number of distinct poker hands is 2,598,960. We already calculated it. And it's this 52C5 value. So the denominator is 52C5. We already know that. The numerator, the number of poker hands with value less than 10 for every card. So what is left to do is to find the number of poker hands with value less than 10 for every card. Then we substitute that value above to get the answer of what the probability of this event B is. Okay. So we want to find the number of poker hands with a value less than 10 for every card. Okay, so let's think what happens. So imagine you have all 52 cards in the deck in your hand again, right? And you spread them out on the table face up so you can see all 52 cards. None of them are blocking any other cards. So all 52 cards are on this table. Okay. We want a poker hand where every card has value less than 10. So let's get rid of all the cards that don't have value less than 10. Okay, so we only want cards left with value less than 10. So what cards are they? So these are the values, right, that are less than 10. Ace, 2, 3, 4, 5, 6, 7, 8, and 9. Each of them have 4 suits: hearts, diamonds, spades, clubs. So each of them has 4 different suits. So we have 9 different values, each with 4 different suits. And so 9 times 4, there's 36 cards whose value are less than 10. So I remove all the other cards in the deck, and what's left in the table are the full 36 cards whose value are less than 10. Their values are ace through 9, and there's 4 of each of those 9 different values. Right? So there's 36 cards. So there are 36 cards whose value is less than 10. These 36 cards consist of the 9 values less than 10 and 4 cards and 4 cards for each value, 1 for each suit, for each different suit. Okay, so you have 9 values less than 10, each has 4 suits, and so 9 times 4, there are 36 cards less than 10. Okay, so on the table, all that's left are the 36 cards whose value are less than 10. Everything else is removed, and those cards have value at least 10. So now the question is, how many ways can you choose 5 cards from those cards, right? Now you're only looking at the 36 cards whose value are less than 10. And so the number of cards, the number of poker hands with value less than 10 for each card, well, that's just equal to, not that. So you have 36 cards on the table. So there are 36 cards whose value are less than 10. You want to choose 5 of them. So 36C5 are the total number of ways to choose. So you might have meant 36 choose 5 by 36 over 5, Anna. So 36 choose 5, right? Yeah, so that's how you would say it. You say 36 choose 5. This is not a fraction. You probably know it's not a fraction. You just didn't know how to say it. But yeah, so 36 choose 5 would be the way to pronounce it. 36 choose 5. Okay, so good. Okay, so yeah, so that's the number of poker hands with value less than 10 for each card. And so you just substitute that here. And so now we have the probability of a poker hand where every card is less than 10. And so if you calculate both those numbers, we already got the denominator in part A. That was 2,598,960. And the numerator, 36C5, is just, well, you multiply out this, you multiply this thing out, you get 36 times 35 times 34 times 33 times 32, and then you divide it by 5 factorial, right? That's the numerator. And then when you do that division, you get 0.145. Okay, and so the probability of getting a poker hand for all the cards at value less than 10 is 0.145. That's 14.5%. So that's part B. Find the probability of a poker hand with value less than 10 for every card. Okay, part C of this problem is find the probability of a poker hand such that all cards have the same suit. You mean, can you leave it as this fraction? So you can leave it as a simplified fraction, but not as, your answer can be a simplified fraction, but I don't want this as your answer. I want you to do the calculation and get that number, right? Get the final answer. Right, so don't leave it as this, but if you want to calculate this and then put it to reduced form, that's good too. Okay, so part C, find the probability of a poker hand. Yes, I answered your question, right? So your answer can be as a fraction, but as long as it's a simplified answer, right? This is an answer, no. If you have this as a fraction, yeah, but no. I don't want it as this either. I would want you to simplify as much as you can. Okay. I don't want you to waste time on a test, though, doing that. If you have your calculator, you can just calculate this and get the decimal, and that's fine. Okay, so part C, find the probability of a poker hand such that all cards have the same suit. So let's introduce notation again. Let B equal the event of getting a poker hand such that all cards have the same suit. This is called a flush. Okay, so we want to find the probability of this event. So the goal is to find the probability of that event B. So again, just like normal, probability of B is equal to n sub B divided by capital N. N sub B is the number of sample points in the event B, and capital N is the number of sample points in the sample space. Here, N sub B is the number of poker hands such that all cards have the same suit. And the denominator, capital N, is the number of poker hands, So the denominator is simple. It's still the same value we've been calculating. It's 52C5. Just choosing any 5 cards from the entire deck. That's the number of ways to have a poker hand. It's the number of poker hands such that all cards have the same suit. Okay, so the question now is, how do we find the number of poker hands such that all cards have the same suit? Okay, and so the answer is, let's think of a process in which we can get any such poker hand. Okay, by process, this is what I mean. So the poker hand you want is 5 cards where they're all the same suit, meaning they're all hearts, all 5 cards are hearts, or all 5 cards are clubs, or all 5 cards are spades, or all 5 cards are diamonds, right? So you want one of those things to happen. So in order for that to happen, so first, step 1 is you choose a suit. Okay, you choose a suit. So your flush, your poker hand where all the cards have the same suit, it's going to be a particular suit that's repeated in the whole hand. So step 1 is you choose a suit. So so you have 4C1, which is equal to 4 many choices for a suit, right? So you have that many choices for a suit. Once you choose a suit, step 2 is you now have a suit. Let's say you chose hearts. Then look at all the cards in the deck that are hearts. Well, if there's 1 heart for each different value. So there are 13 values in the deck. Each one has exactly 1 heart. And so there are a total of 13 cards that are hearts. Okay. So step 2 is choose 5 of the cards that are hearts to make your poker hand. Okay, so it's choose 5 of the cards, not hearts. Choose 5 of the 13 cards in the deck that are the same suit as the one you chose. Okay, so if you chose hearts, it would be hearts. If you chose spades, it would be spades, right? So, so you have 13 C5, and so 13. You have 13 C5 many choices of 5 cards of the selected suit. Okay, so once you select the suit, there are 13 cards, exactly 13 cards in the deck of that suit. And so to get a flush, you have to just choose 5 of those 13. So you have 13 C5 many choices of 5 cards of the selected suit. To get a flush, both things need to happen. So the number of flushes is equal to the number of ways to choose a suit times the number of ways to choose 5 cards out of 13 of that suit. Okay, and so then that's equal to 4C1 times 13C5. Okay, so the number of flushes is 4C1 times 13C5. All right. So thus, the probability of our event B, which we calculated before, which is n sub b over capital N, is equal to the number of flushes, which is 4C1 times 13C5, divided by the number of poker hands, which is 52C5. This was equal sign here. And this was still unknown at that point, right? So that was the goal. Okay, and so now we found that number. It's the product of those two. And so you calculate each combination, plug them in, divide, multiply, divide, and you get 0.00198. Okay, so 5 decimal points have this equal to 0.00198. That's the probability of getting a flush or all cards of the same suit. Okay, any questions about this? Okay, the next example is example 2.8. So example 2.8 is a certain carton of eggs has 3 bad and 9 good eggs. Okay, so a certain carton of eggs has 3 bad and 9 good eggs. So a carton has 12 eggs in total, right? So 3 bad, 9 good. Hey, what is the probability? Well, it does in this 12. This one is 12. What is the probability an omelet just want to spell this quick. There we go. Sorry. Okay. So what is the probability an omelet of 3 eggs has no bad eggs? Okay. So what is the probability an omelet of 3 eggs has no bad eggs? Okay. So let B equal the event of an omelet with no bad eggs. In this case, there are 3 eggs in the omelet. Okay, so that's our event. So we want to find the probability of that event. That's n sub b divided by capital N. So n sub b is the number of omelets with no bad eggs. And then the denominator capital N is the number of omelets. Okay, so what is the number of omelets? Usually the denominator is easier to calculate. Well, you want to make an omelet with 3 eggs. So you have 12 eggs. And you want to choose 3 of them for your omelet. So 12C3 is the number of omelets where you choose 3 of those 12 eggs. Okay, and the numerator is the number of omelets with no bad eggs. Okay, so if there are 3 bad eggs and 9 good, you have 9 good eggs, right? So what you want to do is you want to make an omelet with 3 eggs in it. After this. Okay, so you have 9 total eggs that are not bad. Well, in this case, good. And so you need to choose 3 of them for your omelet with no bad eggs. So 9C3. So it's 9C3 divided by 12C3. All right, and then so you calculate that. And so 9C3 is the fraction 9 times 8 times, what's the fraction 9 times 8 times 7 divided by 3 factorial. And so that value is 84. Okay, you can cancel out things. So 9 divided by 3 is 3, 8 divided by 2 is 4, 3 times 4 is 12, 12 times 7 is 84. So okay, so you can calculate that calculator and you get that value. 12C3 is 12 times 11 times 10 divided by 3 factorial. And so 12 over 3 is 4. Actually, 3 factorial is 6. 12 divided by 6 is 2. So you have 2 times 11 times 10. 2 times 11 is 22. 22 times 10 is 220. So you have 84 divided by 220. And so that as a decimal, that's 0.38. So the probability of an omelet of 3 eggs, so there's no bad eggs, is 0.38 in that example. Okay, so here we're using combination. What is B? What is the probability of having at least 1 bad egg in the omelet? Okay, Well, the probability of at least one bad egg is equal to 1 minus the probability that there is not at least one bad egg. That means the probability of there are no bad eggs. So the probability of at least one bad egg in your omelet is 1 minus the probability that there's not at least one bad egg in the omelet, or that there are no bad eggs. So then that's equal to 1 minus the probability of no bad eggs. We already calculated. That's 0.38 from part A. So this problem is just 1 minus that. 1 minus 0.38, which is 0.62. So that's the probability of at least one bad egg. Okay, and so that's part B, and then part C is what is the probability of having exactly 2 bad eggs in the omelet. Okay, so let B equal the events of exactly 2 bad eggs in the omelet. So we want the probability of that event B. So that's n sub B divided by capital N, which is equal to the number of omelets with exactly 2 bad eggs divided by the number of omelets. Okay, so the number of omelets is still 12 choose 3, because you have 12 total eggs, 9 bad and 3 bad and 9 good. So you have the total of 12 eggs, and to make an omelet, you need to choose 3 of them. So there are 12 C3 many omelets. And the numerator is the number of omelets with exactly 2 bad eggs. Well, so to count the number of omelets with exactly 2 bad eggs, well, you think, okay, well, how many bad eggs are there? There are 3 bad eggs. So I want to choose 2 bad eggs, right? I want to choose 2 bad eggs because I want exactly 2 bad eggs. But then, don't forget your omelet consists of 3 eggs. So you choose 2 bad eggs out of the total 3, and there's 1 additional egg in your omelet. And so since there's exactly 2 bad, that means the 3rd egg has to be good. And so that 1 egg you choose is out of all the ones that are good, which are 9. So the number of omelets with exactly 2 bad eggs is 3C2, choosing 2 out of the 3 bad eggs, and then also choosing 1 out of the remaining 9 good eggs. So 3C2 times 19C1 is the number of omelets with exactly 2 bad eggs. Okay, and so you calculate, and then you calculate that. And so you get the numerator is 27, and the denominator is 220 still. So 27 over 220 is equal to 0.12. That's the answer, 12%. It's 12% chance that your omelet has exactly 2 bad eggs. Right? And so that's that example. Okay, so continuing 2.3.1, which is on permutations versus combinations. Okay, so we're going to compare the two and ask ourselves, when do you use permutations, when do you use combinations to find the probability of an event? So this example is example 2.10. This is the example of 13 cards, which is a bridge hand, are dealt at random from a standard 52 card deck, which is the same as before. What is the probability that all the cards dealt are red, hearts, or diamonds. Okay, so if 13 cards of bridge hand are dealt at random from a standard 52 card deck, what is the probability that all the cards dealt are red, hearts, or diamonds? Okay, so let's introduce notation again. So let capital A equal the event in which all 13 cards are red. Okay, and the goal is we want to find the probability of that event A. That's equal to n sub A divided by capital N. So it's the number of bridge hands, 13 card hands, in which all of the cards are red, divided by the number of bridge hands, the number of bridge hands, or 13 card hands. Okay, so we want to find the number of bridge hands in which all the cards are red and divide it by the total number of bridge hands. Well, the total number of bridge hands is just, there are 52 cards in the deck, and a bridge hand consists of 13 of them. So if you had all 52 cards out on the table, it would just be the number of ways to choose any 13 of them. That's 52C13. That's the number of bridge hands. Now, the number of bridge hands in which all the cards are red, well, we want to choose 13 cards from only the cards that are red, right? Because we only want our bridge hand to consist of red cards. So imagine having all 52 cards on the table, include black and red cards, and let's get rid of all the black cards. So you have 52 cards in the deck, half of them are black, half of them are red. So there are 26 black and 26 red in the 52 card deck. Get rid of all 26 black cards. So now you're left with all 26 red cards. Okay, so now you want to build a bridge hand using only those 26 red cards. And so since you have 13 cards of bridge hand, you want to choose 13 of them. So you have 26C13 many bridge hands that consist only of red cards. That makes sense? So you want to choose 13 out of the total 26 red cards in the deck, 26C13. Okay, and then so if you calculate each of these numbers, 26C13 is equal to 10,400,600, and 52C13 is equal to 635 billion 13,559,600. And so you divide those two, and you get 0.1638 times 10 raised to the negative fourth power. So it's very unlikely. This is the negative fourth power. So you would move this decimal to the left 4 places. So you would have 4 zeros. You have the decimal point, 4 zeros, and then 1638. So this is very, very unlikely that you would get a bridge hand consisting of all red cards. Okay, so that's A. Okay, so part B, answer where the sample space consists of permutations. Okay, so in part A, we use combinations to calculate the number of bridge hands and the number of all red bridge hands. All the cards are red. So we use combinations in A. Here we're going to find the probability using permutations. So we're going to let A be the same event. So let A equal the event in which all 13 cards are red. Okay, and so we want to calculate the probability of this event, but by using permutations instead of combinations. Once you make a choice of permutations or combinations, you have to stick with that choice throughout the problem. You can't calculate some things using combinations and some things using permutations. Everything has to be done by one or the other exclusively. Okay, so P of A is still N sub A over capital N. That's still the number of all red card bridge hands divided by the number of bridge hands, right? So bridge hand is a 13 card hand from the standard 52 card deck. Okay, so we want to calculate these two values using permutations instead of combinations. So how do you do that? Okay, so imagine you have all. So I guess let's talk about the number of bridge hands first. Okay, so you have your 52 cards in the deck, right? And you want to make a bridge hand, which consists of 13 cards. So to do that, you just count all the ways to do that. So you have 52 choices for the first card, times 51 for the second, times 50 for the third, times 49 for the fourth, times ... times, and you want to choose 13. So that's 52 minus 13 plus 1 for the last product. So 52 minus 13 is 49, and plus 1 is 50. So this last number is 50. 52 minus 13 plus 1 is 50. So this is the product of the numbers 52 times 51 times, 52 minus 13 is 39, plus 1 is 40. This is 40, okay? So it's 52 times 51 times 50 times 49 times 48 times 47 times 46 times 45 times 44 times 43 times 42 times 41 times 40. That's this product, okay? And the ... means you're multiplying by all the things in between, right? We're continuing the pattern that we started here by decreasing by 1 each time. Okay, if you change the pattern, you're changing the meaning of ... Okay, so that's the number of bridge hands by permutations. Okay, so here what happened was that the value of capital N was equal to 52 P13. That's what this product is. Okay, right, and a reminder, the formula for NPR is equal to N times N minus 1 times N minus 2 times ... times N minus R plus 1. Okay, and so that's what we did here. We just did 52. N is 52, R is 13. So it's 52 times 51 times 50 times ... times 52, which is N, minus 13, which is R, plus 1. And so you get that product here. And so the numerator is the number of all red card bridge hands. So N sub A, all right, which is the number of all red card bridge hands. Well, how many cards are red? There are 26 total cards that are red. So you have 26 choices for the first card in your bridge hand. You have 25 for the second. You have 24 for the third. You have 23 for the next one, times ... times. Well, your card's going to your hand is going to consist of 13 cards. So you want to choose 13 in total. So that's 26 minus 13 plus 1. And so you're multiplying all the numbers from 26 down to 26 minus 13 plus 1, which is 14. Okay, so we're still using the NPR formula. Here, we're using 26P13. That's N sub A. So N sub A is equal to 26P13, which is this expression. Because we just plugged in 26 for N and 13 for R. So 26 times 25 times 24 times ... times 26 minus 13 plus 1. That's the number of permutations in which, in a set with 26 elements in it, where you want to, the number of 13 permutations in a set with 26 elements in it. So what does that mean again? We want a 13 card bridge hand where they're all red, right? You have a deck of 52 cards, half are black, half are red. 26 are black, 26 are red. Get rid of the 26 black, you have 26 red cards, right? You want an all red bridge hand consisting only, so they're only red cards, but we're using permutations, right? So you have 26 red, and you want to know the number of 13 permutations in a set with 13 elements in it. So here you're counting the number of ways to have 13 cards. The red where order matters, where it matters what the first card you draw, matters what the second one is, and so forth. Okay, so you have 26 choices for the first card, then 25 for the next, then 24 for the next, because you've already taken cards, so you lose one choice each time you make a choice, right? For the next choice. So 26 times 25, 24, you choose 13 cards in total. And so the last one has to be the initial amount, which is 26, minus 13, which is the number you choose, plus 1. Okay, and so this quantity is the number of all red bridge hands where order matters. Okay, so now that's the numerator. And so when you calculate that value, so then the final answer is, I don't want to write out the number I have it, but okay, this is equal to 0. You just plug this in your calculator and you get the final answer 0.1638. I think it's clear to see it this way and writing a bunch of numbers down. Times 10 to the -4th power. Okay, and that's the same, right? So we get the same exact value. You can calculate these values. You can calculate this, and you will get this number, and it's exactly the same as this one. So using permutations and combinations gives you the same answer to the same question, and that makes sense, right? Because you can't have two different answers here. There has to be one probability. Okay. Some problems you can use either one. You can never use both, right? You can only use one or the other. Sometimes you can only use one, and you can't switch over to the other one. This is an example of a problem where you could use either one. Okay. But remember, once you choose permutations or combinations, you're choosing whether or not order matters throughout the problem. And so you can't switch from one to the other. Okay. And so that is that example. Okay, so the next example is example 2.11. So if 4 dice are rolled, what is the probability of obtaining a different value on each of the dice? Okay, so part A is okay. So let's introduce the notation again. Let's let capital A equal the event of rolling a different value on each of the four dice rolls. Okay. So what we want to do is find the probability of this event A. So the probability of A is equal to n sub A divided by capital N. And so I'm continuing to write these things out so that you can see the translation here. So n sub A is the number of ways to get a different value on each of the 4 dice rolls. And then the denominator is the number of ways to roll a roll the dice 4 times. Okay, so let's do the denominator first. The number of ways to roll the dice 4 times. So we're talking about a standard dice in which the sample space, right? Oh wait, no, I don't want to say sample space. Just each dice, when you roll it, it could be 1, 2, 3, 4, 5, or 6, right? So, so the number of ways to roll it 4 times would be 6 times 6 times 6 times 6. So this is 6 times 6 times 6 times 6, right? You have 6 choices for each of the 4 rolls, so you multiply 6 by itself 4 times, 6 to the 4th power. Now, the number of ways to get a different value in each of the 4 dice, well, you have 6 choices for the first roll, but since you need a different value, you only have 5 choices for the next one. then you have 4 left for the one after, and then 3 left for the one after that. So it's 6 times 5 times 4 times 3 ways to get a different value each time. And so these first two 6s can cancel, and you can get 5 times 4 times 3, which is 60. 60 divided by 6 is 10. You get 10 over 36. So this is 10 over 36, and this simplifies to 5/18. Okay, and then as a decimal, it's 0.2778, rounded to nearest 10,000. Okay, so that's 5/18. It's half of 5/9. Okay, so that's the problem. That's that. And so here we used permutations. Okay, order mattered, right? We considered a first roll, a second roll, a third roll, and a fourth roll for both the numerator and denominator. Right? It was 6 times 6 times 6 times 6. We were thinking of each row one at a time in that order. Okay, and so we used permutations here, and we got the answer. Okay, note we cannot use combinations here. The reason is not every choice of 4 numbers is equally likely to occur. Okay, for instance, the combination 6, 4, 1, 3, right, does not have the same likelihood as the combination 6, 6, 6, 6. Okay, so if you were to choose 4 numbers, but you can choose the same one, then there's only one way to choose 6s 4 times. You just roll a 6 4 times. It's the only way it could happen. But a 6, 4, 1, and 3, that combination actually has 24 different ways it can happen, because you have 4. You could choose any of these 4 numbers to go first. Then you could choose any of the 3 to go next, then any of the 2 to go next, and then you have 1 choice less. So you have 4 times 3 times 2 times 1. There are 24 orderings of these 4 numbers. And so since there are 24 orderings of these 4 numbers, there are 24 ways to roll a dice 4 times and to get the numbers 6, 4, 1, and 3. Okay, so the choice of the numbers 6, 4, 1, and 3 is 24 times more likely than the choice of 6, 6, 6, 6. Okay, so you can't use combinations because you can't say that every choice of 4 numbers is equally likely. It's false in this example. Okay, and so in this example, combinations is not an option for getting the answer, and so you have to use permutations, and when you use it, you get this answer. Okay. Okay, so that's the end of 2.3. The next section is 2.4, which is on the multinomial coefficients. Okay, so just to start this off, because we're going to have to continue this next time, because we have 10 minutes left. There are n, choose n1 times n minus n1, choose n2 times n minus n1 minus n2, choose n3 times ... times n minus n1 minus n2 minus n3 minus ... minus n sub k minus 1, choose n sub k. And what this product equals is n factorial divided by n1 factorial times n2 factorial times dot 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 times n sub k factorial. There are that many ways. This is a number I'm calculating. There are that many ways to select n1 elements from a set A for group 1, and 2 elements from A for group 2, dot dot dot, continuing, and finally n sub k elements from a set A for group K. And this is where we assume that set A has exactly n elements where n is equal to the sum n1 plus n2 plus dot 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 plus n sub k. Okay, so there are this many ways to select n1 elements from set A for group 1 and 2 elements from set A for group 2, and final dot dot dot, continuing, and finally n sub k elements from set A for group K, and that includes n sub 3 elements from set A for group 3, n sub 4 elements from set A for group 4, and so forth, right? All the in between ones. But this is assuming that your set has n1 plus n2 plus n3 plus dot 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 plus n sub k elements in it. Okay. So, okay, we have 6 minutes left. So let me just illustrate why this would be true. The next time, maybe we can spend more time. If we run out of time, we can talk more about the math itself next time. Let's just talk about the idea of it at the end of this class. So let's say you have a basket or box, whatever you want to call it. So let's call it a box. It's easier to draw a box. Okay, so okay, so you have this box, right? It's kind of broken. Okay, so then so what we want to do is there are a total of n things in this box. Let's go with balls. Okay, so so let's say first we want to choose n1 things for group 1. So we want to make we have these groups, right? So let's say this is group 1. GP for group. So this is group 1. This is group 2. Right? This is group 3. And so forth, up to including the last group, which is group n sub k. Okay, so n sub k is representing group K. Group K. So we have K groups, okay? And so we want to take all the total of n things in here, and we want to move them into these k groups. So let's say we choose n1 many things to go into group 1, right? So we have all the things that make up this box, right? And so these are the things I'm going to choose for group 1, not necessarily 5. There's just some of them. And so if you have a total of n things in the box, you want to choose n1 of them to be in this group. So you have n choose n1 many ways to take n1 of these things and put them into group 1. Next, you take another group of things for group 2. And so how many things are left? Well, you took n1 out. There were a total of n. So you have n minus n1 things left in the box after you put n1 of them in group 1. So there's n minus n1 things left, and you want to choose n2 of them for group 2. So how many ways can you do that? You have n minus n1 things, and you want to choose n2 of them for group 2. So that's n minus n1, choose n2. Next, you want to choose n3 many things for group 3. So there's other things in the box that you haven't chosen yet, and you want to choose those things for group 3. Well, you had n in the beginning. Then you took away n1 many things for the first group. Then you took away n2 many things for group 2. So now what you have left is n minus n1 minus n2 things in the remainder of the box. And you want to choose n3 many of them for group 3. So there are n minus n1 minus n2 choose n3 many ways to choose n3 many things from what's left in the box after you took the purple and brown ones out, after you took n1 things away and n2 things away from a total of n things in the box. So n minus n1 minus n2 things left, choose n3 of them. And you continue this pattern. And so you can see is that you're always subtracting by the next n in the top, right? And then it's that choose the next one here, right? But n1 is for group 1, n2 for group 2, n3 for group 3. So following this pattern, for group k, you would choose n sub k things left for the group k, but n sub k would be the number of things you would choose. Then what would be left was you would have n things originally. You subtract n1. You would subtract n1. You would subtract n2 minus ... and then you would also subtract minus n sub k minus 1, the one before it, right? The one before this one will be n sub k minus, just like the one before n3 is n2, the one before n2 is n1. You stop at n1, you stop at n2. Here you would stop at n sub k minus 1. So n minus n1 minus n2 minus ... n minus n sub k minus 1, that's the number of things left, and you choose n sub k of them. Okay? So actually what's happening here, since n is equal to the sum of all the n's from n1 to nk, n minus all these things is n sub k. So this value is actually n sub k itself. This is actually n sub k, choose n sub k. Okay, so this is the number. Each of these expressions are the number of choices you have for each group. And then to find the number of ways to choose n1 things for group 1, and n2 things for group 3, and n3 things for group 3, and so forth, up to including n sub k things for group k, you just multiply these things out, and all the ones in between, and the product of all these things and the ones in between, that product makes up the total number of ways to select these many things from each of those k groups. Okay, and so this is the expression that I wrote down on Word. Okay, so look at this expression one more time quickly, and then now see what I wrote on Word. That's this expression right here. Okay, and so that's how you visualize getting that. And then if you express each of these factors in the product as a fraction, right? Factorial expressions, numerator and denominator, you cancel out common terms. You'll get that this is equal to n factorial divided by n1 factorial times n2 factorial times ... times n sub k factorial. Okay, so next time we will continue talking about this. Okay. Okay. And so don't forget that the next homework is due next class, right? So I assigned homework 2 for next class. So just stay with me for a minute. Don't leave just yet. I'm going to put something up on the whiteboard. Okay, so homework 2 is due on Tuesday. Okay. And so we have not yet covered all this material. So we don't have to worry about homework 2. Okay, so okay, so reminder, homework 2 is due next class on Tuesday. I assigned it last class on Tuesday. Okay. Okay, so I'll see all of you next week on Tuesday. Have a good night. See you Tuesday. Bye.
Thank you, Professor. Bye. Have a good night.
Good night.